Today I'll be talking about the equations of lines for vectors in 3D. Consider a line L that's floating in the 3D space that extends indefinitely to infinity and beyond. So in the context of this proof, I'm only going to use this line segment over here, which contains the points P, Q, R, and S, points that lie along the line L. And so the grand aim of achieving the equation of line L is to obtain a simplified expression for the position vectors of all the points along the line L, which means all these points that make up the line L, we need to achieve a simplified expression to express the position vector of all of these points. So I'm going to start with point A over here. Now we know that the position vector of the point A is equal to OA, right, or small a with tilde below. And using this point A, we can define the position vectors of other points along the line. So using OP, Q, R, and S, so we have OP, OQ, OR, and OS. We have OP is equal to OA plus AP. Right, and it gets really repetitive, but I'll show you why later. So OQ is equal to OA plus AQ, right? Because OQ, the position vector of OQ, which is this purple one over here, is equal to OA plus this vector over here, which is AQ. Right, and we have OR is equal to OA plus AR. And OS is equal to OA plus AS. Right, and recalling the previous topic about the scalar multiple of vectors, we know that when two vectors are parallel, so let's say we have AQ and AR in comparison, right? These two vectors are definitely parallel because they are on the same line, they're collinear. So this is AQ and this is AR, right? They're parallel, which means that they are actually scalar multiples of one another. But the fact is AR has a magnitude that is greater than the magnitude of AQ, which means that AR can be expressed as a scalar multiple of AQ. Right? It could be 2 times or 3 times, but this number is represented by K, where K is a real number, so K element of real. Right? And in this same aspect, because AQ is parallel to AR, which is parallel to AS, right? AS is this even longer vector over here. Right? AS is also equal to, so we have AS is also equal to a scalar multiple of AQ. So I'm going to use AQ as the sort of base vector. So AS is equal to, let's say, M times AQ, where M is an element of real. Now when it comes to AP is in the opposite direction to AQ. But let's say that AQ has the same magnitude as AP. Right? These two line segments have the same magnitude. Then you could also say that the vector AQ is equal to negative of AP. Right? This is just an example, but you can say that AP is also a scalar multiple of AQ. So in this case, let's call it N times AQ, where N is a real number. Right? Because elements of real numbers can also include the negative real numbers. So in this aspect, you can actually standardize all the expressions to have OA plus a multiple of AQ. In this case, it's N times AQ, N element of real. That's already in the form of OA plus 1 times AQ. OR is equal to OA plus K times AQ, K element of real. And finally, OS is equal to OA plus, what's it equal to? It's equal to M times AQ, M element of real. Really repetitive, but the point I'm trying to drive here is that the position vectors of all the points along line L each have their own unique real number multiplied to AQ. So if I want to reach point P, I need to multiply AQ by a real number N, and for R I need to multiply by K, and for S I need to multiply by M. So all the position vectors, I'll standardize all these to have to be equal to this small r over tilde below, the resultant vector, and that's equal to OA plus a real number times AQ. So this real number lambda encompasses all the possible real numbers that you can multiply AQ by, which is in fact every possible number in the real number system. And they'll give you different points along the line L, which stretches indefinitely, right, to infinity and beyond. And thus I have obtained the overall equation, which is R is equal to A plus lambda B, where lambda is a real number, where A is the position vector that brings you from the origin to the line. So it's sort of like the first vector you need to use to get to the line. right? You could actually use point Q to get OQ to get to the line. You could also use OR. Right, but all in all, you need to get to the line first. And you need a parallel vector along the line. So in this case, I used AQ, but you can also use AP or AR. It wouldn't matter. So B would be a parallel vector to the line. And these two are the only modifiers that would give rise to a vector equation, right? If you have a different position vector and a different parallel vector altogether, right? Let's say we have a different line over here. Let's call this line M. Right? You would have a different position vector. Or let's say we have a pointer B over here. You need to move the vector OB first before you move parallel to the line M, right? And this will give rise to a totally different equation of a line altogether. Let's say we have 2 points A and B given by these coordinates, and they have line L passing through them, and we have to obtain the equation for L. So let's assume that line L doesn't pass through the origin first. To get to the line L, we first have to move the position vector to the line L. And that's either point A or point B, right? Because you can move to the line L, or it doesn't matter which position vector you use. I'll show you that the equation is the same later on. So let's choose OA first. We have the position vector being OA, and that's equal to 1, 3, 2. And the parallel vector would be, well, there's only one available, which is AB. And that's equal to OB minus OA. And the right hand side letter minus the position vector of the left hand side letter, right? OB minus OA, which is equal to -1, -1, minus 1, 3, 2, which gives you -2, -2, -3. Oh, but I don't want to use the negative signs. Well, in fact, it doesn't really matter in the vector equation. So I can choose 2, 2, 3 instead. So I have obtained the vector equation, which is R is equal to 1, 3, 2, position vector plus lambda times 2, 2, 3. Right, which is the parallel vector. And the reason why I could eliminate the negative sign is because if I use the negative sign for the parallel vector, let's say it was -2, -2, -3, right, then that would be R is equal to 1, 3, 2 plus lambda times -2, -2, -3, right? And this would be equal to 1, 3, 2 plus negative lambda of 2, 2, 3, which can be substituted by another real number plus mu times 2, 2, 3, where mu is a real number. So in fact, it's just extra work for yourself because you're eventually going to change it to simplify the expression further. And now let's use OB and show that using OA is the same as using OB. Right, so let's say OB is being used. We have R is equal to position vector of OB, -1, 1, -1, plus lambda times 2, 2, 3, the parallel vector, where lambda is an element of real. And this is the same as having -1, 1, -1, plus lambda minus 1 of 2, 2, 3, plus 2, 2, 3, right? So I'm just taking away one of the 2, 2, 3's out from the lambda, and this gives you -1 plus 2, 2, 3. So that gives you -1 plus 2, 1 plus 2, as well as -1 plus 3, plus lambda minus 1 times 2, 2, 3. And this gives you 1, 3, 2, which is the position vector of OA. So we get back the position vector of OA plus lambda minus 1, which can be substituted by another real number altogether, which is mu, which is going back to square 1. So essentially, all you need for the vector equation of a line is just the position vector of a certain point that brings you to the line, as well as a parallel vector that allows you to maneuver along the line L.